Hi guys, let's do a second disorder structure. We can jump right into this one. We have a model mostly built already. We'll take a look in a text editor. And at the same time, we'll run a refinement quickly. Oh. We can see, looking at our inst file, that we have all our atoms organized, kind of grouped up by parts of the molecule. We have a nice instruction to make everything anisotropic, and we have hfix instructions to add all of our hydrogen atoms. Let's take a look in OLEX. This is a bicyclic silicon-based molecule. Orange is silicon here. We have a methyl thiomethylene linker group on each end of the molecule. We can see that the biggest difference feature in the structure right now is a Q peak of 2.4 electrons near one of these sulfur atoms. This is kind of a flexible group, so there's a very good chance that we're looking at a disordered second position of the methyl thio end group. Over here, another large Q peak is 1.2 electrons, and that's in a very similar position near the other methyl thio group. So there's a good chance that we're going to be looking at a disorder of both the methyl thiomethylene end groups here. Everything else you can see by looking at the difference features, the ADPs. It's a pretty stiff molecule, and it looks like everything is pretty much locked in a single conformation. So that's not unexpected, but it is nice, and it's going to make it easier to focus in on the parts that we actually need to look at here. So let's get started on the disorder of the more significant disorder, which is C14, S15, C16. We're going to start by making these three atoms isotropic. I'm going to do that in this example with an nice 0 instruction above the first one and a plain nice after the last one. I'm going to get rid of the hydrogen atoms on those two carbons. So C14, get rid of that, and C16, and get rid of that too. And we'll turn down the occupancies on these three possibly disordered atoms just a bit in this case. It looks like not such it's not very close to 50-50. It's a pretty unequal disorder. So in this example, maybe I'm going to make it part 1 70% occupied. And I'm not going to forget part 0 at the end. Let's run this refinement. All right, what are we looking at now? This might have come out a little strange. I can see now the two biggest difference features. It's not two disordered positions of this atom. Instead, it's just the anisotropic vibrations of this atom are coming back as big difference features. Let's try and get that other Q peak back by just drawing more Q peaks. That's on the plan instruction near the top of the file. I'm going to make 60 Q peaks. Repeat the refinement. Check this out again. Well, it still won't come back. So let's try using these two Q peaks as the two positions for this group, but we won't be surprised if it acts a little weird. Okay. Second position, I don't see any disorder of carbon 14, so we're going to leave that out for now. S15, we're going to use Q1 on the right here, and C16 is going to be Q3. We'll come over here and make those changes. I'm going to put the part instruction after C14 now. We're going to say that C14 is ordered as far as we know. We do need to put a same instruction, which is going to go in front of C14. That's going to be same C14, S15B, which we haven't made yet, C16B. These 3 atoms are going to match the 3 atoms immediately following the same instruction. Instead of part 0, now we're going to have part 2. We'll go ahead and refine these occupancies right away. Part 2 is going to be minus 21. S15B, sulfur is atom type 4, and the coordinates are over here. 817, 1.008, 653. C16B, got the coordinates here. Now part 0. And this anice instruction, I'm going to shift it down. Part 2 has its occupancy refined now, so we better change part 1 to match. This is going to be 21 since the other one is minus 21. We're going to go up to the FVAR line, make this a 70-30 disorder to start, but that number is going to get refined. And we'll try running this refinement. Bad atom or unknown instruction. What does that mean? Oh, I see the problem. Well, you know what? Let's figure out the problem so that we can see how to deal with something like this. Let's take a look at disorder 2.list. This file is going to have some instructions about some description of different parts of the refinement. You can see here that we got to atom C16B, and then we threw a bad atom warning. What's wrong with C16B? It's missing its scattering factor type. Go down here. Before the first coordinate, we just need to stick a 1 in there. Now we should be fine. Get rid of the list file. Try the refinement again. Now it works. Let's see what this looks like. Okay, this is pretty much what we were afraid of here. The the second position of this disordered chain, it didn't come over here and land on this big Q peak. Instead, it's stuck right next to the first position of this chain. So let's take these coordinates. We weren't sure if we had them right the first time. We'll enter these coordinates. S15, these are pretty different. This is going to be 0.778, 0.69, 0.62. And I'll enter C16 also with the Q peak farthest to the right here. Save this and run it again. How does this turn out? Oh, what's going on? It walked right back over and landed on the same position. Looks like it really likes to be there. We could see in our isotropic model that there were some big difference features around the more occupied S15. So maybe we should make that atom anisotropic so that it can take care of its own difference features, and the new atom S15B won't be tempted to wander over here and try to help with those difference features. So I'm going to come back and make the major part of the disorder anisotropic. In the anice 0 instruction, I'm going to put it just before the minor atoms in the disorder. Let's see what this does. Take a look. Okay, great. Now part 2, I scrolled down to get rid of my Q peaks, clear it up a little. Now part 2 is over here where we wanted to go. What's the ratio of this disorder? Part 2 is 9% occupied. That's I mean that's okay. We can see that the isotropic ADP on the minor part it's a reasonable size, so that means the occupancy is probably about right, and it's not strange to have a 90-10 disorder. Let's check the geometry. Especially, I'm a little worried about the difference in this carbon-sulfur bond versus this carbon-sulfur bond. The big one is 1.79. I happen to know that's about right. The minor component is 1.57, which is way off. So that's a sign that probably carbon-14 should be split as well. The reason we didn't see a difference feature for carbon-14, maybe it's just because it's only a 9% occupied disorder. So we'll go ahead and split that just based on the fact that we're looking at impossible molecular geometry in the minor part. So right above S15 and B, I'm going to put a C14 of B, and I'm just going to use C14A and change its name. We need to fix up our same instruction, and now the last ordered atom is silicon 11. So the same instruction, I'm going to take it from here and put it above silicon 11. And now the atoms covered by the same instruction are going to have to include carbon 12 and carbon 13, just because unfortunately they're in between the last ordered atom and the atoms that we're actually interested in. So now silicon 11 through carbon 13 should be the same, and then carbon 14 through carbon 16 should match carbon 14b through carbon 16b. I can see a couple little errors that I need to clean up right now. First, C14, this should go inside the disordered part now. C14b got the wrong name. And is there anything else? Let's run this refinement and see how it turns out. Before we do that, I will add a simu instruction for overlapping ADPs like we've done before. We'll put the same uncertainties and maximum distance as we did before as well. So I saved that. I'm going to refine it again. How does this look? I'm going to kill my Q peaks. Okay. How about this carbon-sulfur distance? Now it's 1.8 angstrom. These match each other, so that's a good sign. The displacement parameters on the minor component of this disorder, this is a common problem. We can see one, it's not crazy, but a bit big. This carbon atom, the displacement parameter is way too small. That's not a sign of too much electron density on that position, as much as it is just, now we're looking at 9% of a carbon atom, which is less than 1 electron. So there's not that much scattering to define the displacement parameters here. Let's see if we can control this with a restraint. I'm going to go next to my same align. I'm going to put a RigU restraint on the major part of the disorder, which is silicon 11 and C14 through C16. And the minor component is isotropic right now, so RigU is not going to work. Instead, I'm going to put a simu restraint with the default parameters. I won't write any numbers. I'll just write silicon 11 C14b through C16b. Save this and run it again. See if it helps. no, these displacement parameters are not stabilized at all. It's not. It doesn't make me worry about the quality of this model, but you don't want to be publishing strange-looking displacement parameters like this. So we better take some other action to make them more reasonable. We can start by adding our hydrogen atoms back in. If there's one hydrogen on this carbon that happens to be sticking over in this direction, it's actually going to have pretty comparable scattering power to the carbon that we have there. So we better put that hydrogen on there and just make sure that that scattering is accounted for. We'll make a couple new HFix lines. We're going to do HFix 2,3 for the methylenes, C14 and C14B, and a rotating methyl group for the major part of the disorder, C16, and I'm gonna do a staggered methyl group, not freely rotating, HFix 3,3 for the minor part, C16B, since we know there's just not going to be enough scattering to locate those hydrogens. Run that refinement and take a look. Okay, the hydrogens went where they belong, but we still have this issue with C16B looking way too small as far as its displacement parameter. So, you know, we would like it if we could refine anisotropic ADPs or independent isotropic ADPs. Sometimes the data is just not there. We talked about not enough density to find very much detail in a less occupied component. So we're going to go to something called a group isotropic ADP for these atoms. We're going to set the isotropic ADP for all three of this minor component to be equal to a free variable, and then they'll refine together. I'm going to do that by changing the last number on this line to 31, which means 1 times the next free variable that we haven't used yet. We used number 2 for the occupancy ratio, so now we're going to use number 3 for the ADPs. On these lines, I have to put in occupancy, but it's going to get ignored by the part instruction. So I'll just put 11. I'll put a 31 for the displacement parameters of all three of these atoms. Now we have to come up and add a third free variable. We'll put 0.05, which is a pretty typical isotropic ADP. Save this. We're going to keep an eye on the R factor and just make sure that it doesn't skyrocket when we take parameters out of the model like this. So right now we're at 5.46%, and we'll see how it changes. It went up to 5.47%. That's nothing to worry about. And our model looks a lot more reasonable now. We have all three of these atoms in the disorder. We told them to match, so we're not surprised that they match, but we are happy that they look pretty comparable to the major component. This has a U factor, ADP of 0.035, and the major component has an equivalent isotropic U factor of 0.37. They match perfectly. So that's fantastic. Our hydrogen atoms are on there. Final ratio is 91 to 9. Everything looks good there. Let's come over here. There's still one large glaring difference feature in the Fourier map, and it's a similar looking disorder of the second methylthioethylene group. Now, this is one electron. That's compared to a sulfur atom, 16 electrons. It's going to be like a 5% occupied. disorder. Instead of going through the whole thing, I'm going to use a shortcut here and just, first I'm going to kill hydrogen atoms. I'm going to grab these 3 atoms, type mode fit. Now I can move this whole group around by hand just by dragging it in OLEX. I'm going to control click on the first atom, make it a pivot atom, and then the rest of the group I'm going to drag it over here and try to get the sulfur on top of that big Q peak. So we can see how we used mode fit to just grab the group and physically move it over. And instead of saving this model, we're just going to take these coordinates and use them as the second positions of sulfur 45 and carbon 46. So I'm going to come down here. I see no reason to worry about carbon 44 for now. We'll see how it turns out after we refine this. But right now, it's just S45 and C46 that are disordered in part 1. We're going to use our next unused free variable, which is number 4. There's a part 2. This is minus 41. And the atoms are going to be S45B 127.277.792 and C46B with these coordinates. Part 0. We need a same instruction. It's going to go in front of the last ordered atom, which is C44. It's going to be same C44, S45B, C46B. And it's probably fine to refine the major component anisotropically, but we want to make sure that the minor component stays isotropic. So I'm going to put anis 0 in front and anis after. Let's try to run this refinement. We didn't set our free variable for atom S45, which is free variable 4. We'll put in a 0.9 here. Let's run this and see what it looks like. This is a good sign. We can see that the highest peak is now 0.43 electrons. It was 1.2 electrons before. Let's take a look at the res file here. Okay. There's a couple problems that I can see. First, what's going on with this hydrogen bonded to the sulfur? It's the same problem that we talked about in our first disordered structure. It's a little more pronounced this time. But these hydrogens in part 0 don't belong with this sulfur in part 2. Instead of one set of hydrogens on C46, we need to, or C44 rather, we need to make 2 pairs of hydrogens, one to go with the major component, one to go with the minor component. We'll come back to that. For now, let's take a look at the geometry of these atoms. 1.79 is good for this carbon-sulfur distance, and 1.82, that's also fine. The displacement parameters, they look a little weird. This is only 4% occupied. Frankly, we're not going to get any information about the displacement parameters of a 4% occupied carbon atom. So let's go back here and we'll go ahead and use another group isotropic ADP for these atoms. Do the same as before. I need to put a site occupancy even though it's going to get ignored. And then I'm going to put free variable 51 is our group isotropic ADP for these 2 atoms. We need to go back to the free variable line and put a number here. We'll try 0.5 as a starting point again. And everything else, oh, the hydrogen atoms. I'm going to go up to the HFix line. I'm going to get C44 off this line. Where is it anyway? Oh. This whole line only has C44, and we're not going to do that anymore. Instead, C44 is going to be followed by part 1, 41, one pair of affixed hydrogens. I'm going to remember to use a writing displacement parameter. I'm just going to repeat the same and fix up the parts that I need to fix. This part is now part 2 minus 41. And the atom names are C and D, and everything else should be the same. Okay, let's run this and see if it seems happy. Okay, so let's see. Now our difference features are plus 0.43, minus 0.56. That's a great sign for a structure of this composition. We have some heavy-ish atoms, so it's fine to see features of that size. We should be happy. How does our new disordered part look? It looks great. The ADPs are the way we left them. We're missing hydrogen atoms on our less occupied C46b, but the geometry is totally reasonable, and now we don't have that little hydrogen atom problem anymore. So I'm just going to go back and add my hydrogens to, what is it, C46b. I'm going to lock those in a staggered conformation because we know we're not going to identify the torsional angle there. C46b. Let's write this, refine it, check that everything is still okay. This looks great. We can refine the weighting scheme. I'm not going to bore you with too many rounds of this, but I want to see what happens to the difference map after one round. It did get a lot flatter. It went from plus 0.4. Oh, you know what? It's almost the same. The R factor, make sure this is good. R1 is 5.2%, and we compare that to R int 5.4%, R sigma 5.6. That's exactly what we should see. The refinement is almost converged, but not quite. We still have 0.078 maximum shift over ESD. So we'll run a couple more cycles here. Make it 20. Refine that. Now our shift is essentially 0. The goodness of fit is close to 1. The R factor is good, as we discussed. The geometry is good, so we're finished with this disorder model. Thanks for watching.